Hi, thank you for watching. My name is Boris Kaus of the Johannes Gutenberg University in Mainz. And in the coming minutes, I would like to give you an overview of the research we have been doing in trying to use geodynamic models to test plate tectonic scenarios of the Mediterranean-Alpine area. This work was done in collaboration with Eline Le Breton of the Free University in Berlin and with Christian Schüller, who is a master student in Mainz and who did most of the simulations I will show you. I think all of you are aware of plate tectonic reconstructions, and this is an example of the work of Eline and co-workers, where she developed the plate tectonic construction to show how the Alps evolved with time. And such reconstructions are consistent with geological and geophysical data, including paleomagnetism, and they give possible scenarios of how the Alps may have evolved. They are not unique. There are other research groups that have different reconstructions for the same area. And these kind of reconstructions are purely kinematic in the sense that they are consistent with how the plates deform on the surface of the Earth, but they are not necessarily consistent with the physics of how the lithosphere and the mantle deforms. And one of the interests of us was to figure out to which extent these plate tectonic reconstructions are actually consistent with fully dynamic models. And in order to do this, we have performed 3D geodynamic simulations using LAMEM, the code developed in Mainz, which is based on a staggered finite difference and Mark-on-set approach, which uses viscoelastoplastic rheologies and laboratory-based creep laws. And the general approach is that we draw the setup and map view in Inkscape. We indicate where the subduction zones are 20 million years ago, what the angle was of the subduction zone, what the length was of these plates, and we use that to reconstruct in 3D how the plates may have looked like, and from that we reconstruct a 3D thermal model and a 3D model that shows you where the different rock types are. We then run these models for 20 million years into the future and vary the various parameters and compare it with the present day observations. Just to give you the idea, the resolution is about 16 by 12 by 5 kilometers for every grid cell. We have 3 slab lateral boundaries. We have a no slab lower boundary and a free surface at the top. That means that the internal dynamics is mostly due to slab pull, perhaps ridge push. In some simulations, we also simulate the effect of Africa being pushed northwards. So we have performed systematic simulations, and I will show you the results of some of these simulations to give you an idea of the sensitivity of the results to variations in the parameters. Let's have a look at the reference model. This now shows you a map view where you see the Adriatic slab, the Hellenic slab, and the European slab, and the Gibraltar slab. And if I run this forward in time, you will see that these slabs retreat. The Adriatic slab and the Hellenic slab meet south of Adria after 20 million years approximately. The European slab breaks off, but it's still attached here in the Carpathians, and also the Gibraltar slab retreats. So just to show you a zoom in, Adria moves a little bit northward. We have a first break-off event in the Alps, and we seem to get we start to get a second break-off event here. Just to give you the idea, every simulation takes about 16 hours on 128 processors, and visualization is done in ParaView. Okay, some of the key features of these simulations is that we have a tearing of the European slab, which always starts around here, around the Bohemian Massif, and then propagates laterally. It becomes shallower here in the Carpathians. This is mainly due to the change in the geometry of the subduction zone, and not because of the Bohemian Massif, because this area has actually the same properties as the European plates outside. One of the other features of our models is that the Apennine slab always retreats quite fast, which is due to having an old oceanic lithosphere here in this area, in the dark blue area. And it breaks off in the northern Apennines, and then moves, this break-off moves southwards. And we are well aware that this is inconsistent with the seismological observations, which suggest that there is a continuous subduction zone in the northern Apennines, and perhaps only a slab gap in the central Apennines. And one of the features is that the Carpathian, European slab is still attached in the Carpathians in the east, and partly attached in the Western Alps here. Okay, so what happens if we change other parameters? And one of the important parameters are related to the viscosity of the mantle. And it turns out that this affects the timing quite drastically. And a creep law viscosities of the olivine rocks or peridotite rocks always have a parameter called the activation volume. And this parameter is very poorly constrained from experiments. In the reference model, we use a value of 9 times 10 to the minus 6. If I change that to 5 times 10 to the minus 6, what you see is that things evolve much more rapidly. And we get a slab break-off event of the European slab, we get a break-off event of the Hellenic slab, all within 9 million years. If I, on the other hand, increase this value a little bit, you see that things take much, much longer. So even after 25 million years, the Hellenic slab has hardly retreated, and the European slab is still attached here. So you see that changing this parameter by a little bit can have a very drastic effect, and experimentally all of these values are valid. Anything between 5 and 20 times 10 to the minus 6 is reasonable. So it turns out that the timing of these kind of simulations can be tuned by changing the activation volume, and this is one of the things that geodynamic modelers do quite a bit. And what we have done here is we have taken this as a reference simulation, because this resulted in the Hellenic and the Adriatic slab meeting south of Adria after about 20 million years. But it also means that very precise timing information is kind of difficult to get from the geodynamic simulations, because there is always this inherent insecurity on what the material parameters are. So what happens if I vary other parameters? What if I push Africa, which is shown here on the right? You see that the geometry changes a little bit of the Gibraltar slab, but otherwise we have hardly any effect on the model dynamics. And this does suggest that Adria is mostly driven by the internal dynamics and not so much by the far field push of Africa. What happens if we have a mid-oceanic ridge here? So in the reference simulation we include this ridge, but it is actually not clear whether there was a true oceanic crust or not. And the latest results of the Ligurian Ocean seem to suggest that there is no oceanic crust exhumed here, but that the mantle is directly exhumed at the sea surface. And that suggests that there was a lot of stretching, but no formation of new crust. And if we do a simulation where we do not take this mid-oceanic ridge into account, it actually changes the dynamics quite a bit. On one hand, Sardinia and Corsica do not move an equal amount to the east. On the other hand, the retreat of the Gibraltar slab is more than in the other simulation. If we include the oceanic ridge above the retreating Gibraltar slab, then you get similar effects, but you have still an eastwards motion of Corsica and Sardinia, and you see here that these islands are moving a little bit too far towards Gibraltar. So this affects the retreat of the Gibraltar slab, and it affects the motion of Corsica, Sardinia. What happens if we change the dip angle, the initial dip angle of the European slab shown here? In our reference model, this is rather steep, 80 degrees. If I change it to 70 degrees or 40 degrees, you see it changes the evolution in the Carpathians quite a bit. We have less break-off, but in the Alps it doesn't do all that much. What if I change the thermal age of the continental margin that is shown here? So this was likely a thickened continental crust prior to the collision. And in a reference simulation, this was 80 million years. If I make this a bit smaller, if I use a half-space cooling age of 40 million years instead, you see that the slab here, the European slab, breaks off a little bit easier. And if I use an older continental age, you see that this has a quite drastic effect, because we have hardly any retreat of the European plate, and also the Hellenic slab has hardly retreated. So the properties of the overriding plates have a significant effect on the subduction dynamics in the area. And that is because it changes the mechanical state of the overriding plate, and it doesn't allow for rifting and retreat as easily as in other cases. So in our reference simulation, we did not include a slab north of Adria. There is some discussion on whether this slab existed or not. So let's have a look what this does if we include it. If we include a slab, you see that it actually drags Adria towards the north, which you can even see better in the perspective view here. So it actually affects the motion of Adria quite a bit. And if I now compare this simulation with our reference simulation, you see it does move Adria more to the north. If I have a simulation in which I also include a slab not only to the north but also one to the northeast, you see that we move Adria more towards the northeast. So the effect of having these slabs is that it drags Adria into the different direction. In this particular case, it actually drags it away from the Alpine chain, and that is likely because there was no slab in the Apennines to counteract this motion. So what happens if we start changing the properties of the continental margin of Adria, which is this yellow area here in the map view? The reference simulation, this is 40 million years old. If I take an 80 million years or 120 million years old thermal age, you see that it changes the way in which the Apennine slab breaks off. So if I have an older age, it is attached for longer before it breaks off, and I have an even older age and an even stronger plate, then it is attached even longer, and there is even a continuous subduction in the north and a slab gap that starts to appear here in the south. So this suggests that that this is a rather important parameter that should be taken into account. In this particular case, the Apennine slab did not retreat sufficiently south and didn't meet the Hellenic slab yet. So that is something to be tested. So this brings me to the end, and just to give you a summary, we have performed 4D geodynamic models starting from plate-tectonic reconstructions 20 million years ago, and we ran them forward in time. And generally, these simulations highlight the importance of changing the geometry, changing the rheology and the thermal structure of the plates on the evolution of this. They also suggest that the push of Africa is likely not the main force driving Adria, but that it is rather driven by internal dynamics. And many aspects of the models are actually reasonably consistent with observations. The retreat of the Gibraltar slab, the retreat of the Hellenic slab, the evolution of the Carpathian slab, and even part of how the Alpine slab is pretty much vertical in many simulations seem at least halfway consistent with observations. I'm not saying that it is fully consistent because the Gibraltar slab should have retreated more, etc. So details still need to be sorted out. Yet there are also some problems with the simulations, and that is that we do not get the highest topography in our models where the present-day Alps are, and we do not get an elevated topography where the Apennines are nowadays. So I think some work still remains to be done to fine-tune these models, but I think these simulations show that it has now become possible to test such plate tectonic scenarios with fully dynamic geodynamic simulations, and I think that this makes many testable predictions. So I think it's interesting to have a look at this. Thank you very much for watching, and please leave a comment or write me an email if you have questions. Thank you very much.